Hi everyone, my name is Joyce. I'm a software engineer working in a team that deploys machine learning techniques to government sectors. Today I'm going to talk about a common problem in machine learning known as covariate shift. So let's do some motivation first. Say you are doing a speech recognition project. It might take you a huge amount of time and money to finally get a dataset that is ready to train different models. And luckily, you managed to get a best model that gives you the average validation accuracy of 96% after cross-validation. Everybody is happy with this, and then you decide to put this model into real-life production. So millions of dollars were spent to deploy this model into vehicles. However, after 1 month, you got many complaints that this model is not working. So you start an investigation and get a query set. You found the accuracy on the query set is as low as 67%. And no matter how complicated model you have tried, you always get that kind of low accuracy. So what is going on here? It turns out that the voice in the training set only got the voice of human. However, in the query set, you got the mixed voice of human and the background vehicles. So given our model has never listened to the voice of vehicles, it is understandable that why the accuracy on the query set is that low. So this is a very classic example of covariate shift. This is the outline of today's talk. I would first talk about what is covariate shift, why would it occur, and what consequence would it have. Then I will talk about ways to detect the covariate shift. We have visualization method and the quantitative method. Lastly, I will talk about 2 strategies to handle covariate shift. So the formal definition of covariate shift is that when the distribution on the training and the query or test set do not match, we are facing the covariate shift or sample selection bias. So this is apparently against the fundamental assumption of supervised learning that both the training and the query set should be drawn from the same population or distribution. So basically, we have this distribution mismatch problem. Look at the left-hand side. The green line shows the density of training dataset, and the orange line shows the density of query set. You can tell from this distribution plot that they come from the same distribution because their density looks almost the same, which is always assumed for supervised learning. Well, in the right-hand side, you can see the density of training and query are completely different, which means they come from different populations. So we have this assumption violation for the supervised learning. Actually, covariate shift is very common in real-life projects. Say your training sample generated might suffer this lack of randomness, or due to limited time and budget, you end up with inadequate samples. For instance, we all know it's very expensive to get samples for medical-related projects. Apart from that, the sample you get might be selected from very biased rows. Say you only got samples from Victoria State, then it would be very biased if you are going to generalize your model to the whole Australia, because apparently the features on the rural area would be very different from the features on the urban areas in Victoria State. So there are 2 major consequences the covariate shift would have. First, the model you trained might overfit on the training examples, and the predictions on the query set might be unreliable. Say we have this binary problem. In the left-hand side, we have this ground truth, where the orange points are the dataset with label 0, and the blue points are the dataset with label 1. You can see the training set mainly located in the middle part, whereas in the query set, they locate on the upper and bottom part. So our classifier might learn a wrong decision boundary, shown as this red dashed line. You can see it wrongly classified nearly half of the query set. If the classifier got a chance to see the points on the upper or bottom part, then it might be able to learn this optimal decision boundary, shown as this green dashed line. So it would be always a good practice to detect a covariant shift in the first place. Many people might not bother to do this and jump directly to the machine learning part, but this will create potential risks if you are going to apply your predictions into real-life project. So here I want to talk about 3 ways. We got visualization, membership modeling, and uncertainty quantification. So the most straightforward way is to plot both the training and query set together and see if it's obvious that they got different distribution. And you might ask me, what if I got high dimensional data, which is always the case in real life project? So I would first recommend a per dimensional visualization if your features are not like 100 or 1,000. After that, we would always do a dimensionality reduction with PCA or TSNE. Then we can visualize dimensionality reduced training and query set together on a 2D plot. But bear in mind that PCA sometimes might hide the potential distribution mismatch. Apart from that, the visualization is very subjective and open to interpretation, which means we need more robust methods to tell us if we got covariant shift. So we got a quantitative method called membership modeling. So the main idea is that we apply a model to predict the probability of a new point being a member of the training set. For example, the one class SVM could classify new data as similar or different to the training set. Say we have our training observations here in the white points, and the one class SVM would learn a frontier shown as this red circle. Then the one class SVM would classify points that are similar to the training set in color purple. You can see the purple points mainly inside the circle or near the circle. And one class SVM would also classify the points that are different from the training set in color yellow. You can see the yellow points located far away from your training observations. Another quantitative method I want to talk about is uncertainty quantification. So we first feed a probabilistic model to the training set. And with probabilistic model, every prediction has uncertainty or confidence interval associated with it. So the concept of uncertainty is that given a new point that is similar to the training set, our model would be very confident about the true target value for this new point, because the model has seen many training points share these similar features. Whereas given a new point that is different from the training set, our model would be very uncertain about the true target value for this new point, because the features for the new point our model has never seen before. Then you can determine the covariant shift by looking at the uncertainty of predictions. So to better demonstrate this idea, I want to show you this regression example. So here we got our training observations in green points. The model would learn a regression line shown as this green line. You can see surrounding this regression line, we got an area filled in the color gray. This shows the 95% confidence interval for your predictions. Then, given a new query point shown there, the model will give you a prediction value shown as this red point. Apart from that, the model will give you the lower and upper bound for your prediction. You can see the bound is very wide, which indicates we have a high uncertainty associated with this prediction. This makes sense. if you take a close look at this query point, you can see the X it got has never been seen by our model, given the training samples mainly located in the middle part. So the conclusion is that if this point gets a low uncertainty, that means this new point is similar to the training dataset. If this new point got a prediction with high uncertainty, that means this new point is different from your training dataset. So after detecting the covariant shift, we need to handle covariant shift. Here, I want to talk about two strategies. The first one is training sample reweighting. The main idea is to make the distribution of training data look like the distribution of query data. The second strategy is active learning. So it basically helps the model gain understanding about the query data and learn effectively. So with sample reweighting, we first build a classifier to classify training and query set. Maybe training data got label 0 and query data got label 1. So for instance, we have this data set where the training data points are in color yellow and the query sets are in color purple. After the classification, the classifier would learn a decision boundary shown as this red dashed line to separate the training and query set. If you look at this plot, I actually colored the training sets with the probability of being inside the query set. You can see some points with light yellow here, which means they got low probability being inside the query set. It's obvious that this light yellow far away from the query set, right? And we got some dark yellow points in the middle. They got a high probability being inside the query set. You can see they almost mixed with the purple points there. So with this probability being inside the query set, for every training sample, we can reweight our training points in the learning process. So the idea is that initially we treat every training point equally, but with the presence of covariant shift, some training points are more important if they are similar to the query set, while some training points are less important if they are far away from the training set. So the probability of being inside the query set would be used as the weight for reweighting the training samples. So hopefully, after reweighting, the density for the training and query set would match, shown as the plot on the right-hand side. So one thing to bear in mind that overlap between distribution of training and query set is essential to apply sample reweighting. Because say if we got an overlap shown as this green circle, if you look at their density plot, this overlap is actually the area where we have the red vertical lines. That means we have some knowledge about the query dataset. In contrast, if the training and query set are far away from each other, then their distribution has no cross-section. Then we know nothing about the query set. And your classifier might learn the weight for every training example nearly 0. Then it won't make sense to reweight your samples in the learning process. So it would definitely eliminate covariant shift if you can get more samples. Well, the problem is, how can you get more samples? We all know it's expensive to get new observations. And compared to randomly getting more samples, we should think of a better way to get the most informative training observations. This is why I want to introduce you the active learning. So the idea behind the active learning is that the model will decide the next observation to receive to most improve the performance. This allows the model to prioritize the area it is most uncertain about. So this flow diagram shows the process of applying active learning. So given the training and query set, we train a probabilistic model, and then we predict for the query set. Then you find the query point that is expected to most improve your performance. For instance, you might select the point which could reduce the uncertainty for the whole query set. Or you want to select the point that could reduce the highest upper bound for your confidence interval. It depends on what kind of thing you want to achieve with active learning. Then get a target value for that most useful point. You put this point into your training cohort, then you retrain your model and repredict. Hopefully, this time the uncertainty level would reduce a lot with this new informative training observation. So to better demonstrate how active learning works in the real life, I want to show you a live demo. So say we want to know the number of government employees in Australia, but due to limited budget, we only have this number in Victoria state. There. So but you want to know this number through whole Australia. What we did is that we apply a model to predict the number of government employees for every local government area in Australia, where the features are some demographic features we have for every local government area. Then remember, as I mentioned before, this approach would have covariant shift problem because our training observations are only from Victoria state. This is very biased because the demographic features in the rural area, say North Australia or West Australia, would differ a lot to the demographic features in the urban area. So before I show you how active learning eliminates the covariant shift, I want to show you the ground truth for the number of government employees in Australia. So we color the map with the quantity. The yellow means high quantity, the purple means low quantity. So this is our prediction in the first round. So we only got training samples shown as these blue points in Victoria state. And this model predicts the quantity for the whole Australia. And remember, we color this map. We color the uncertainty by the transparency of every prediction. So you can see the predicted value are very similar for the rural areas in New South Wales and Queensland. This makes sense because for urban area, they share very similar demographic features. Well, for the rural area, you can see the transparency is a lot because our model is not very confident about the true quantity in the rural area. So our model tells us that you should get the quantity in the Darwin shown as these red points there. And if you get the quantity for the Darwin, you repredict, you can see the differences. So the transparency disappears a lot in the north area. But bear in mind, you only got one observation from Darwin, but the uncertainty level reduced a lot in most of the north area. This is the magic part about active learning. So the uncertain point, it might share same features for not only the position we get the observation, but for the areas where they share the same features. So compared to get a new observation from the New South Wales, apparently get more observation from the Darwin will improve your model a lot. So we continue to the next round. So this time our model tells us we should get sample in the Western Australia. So you can see compared to the ground truth, our model did a great job after getting extra 3 observations. So this is how active learning could help the model learn cost effectively. So let's compare these 2 strategies for handling covariant shift. For sample reweighting, the bad thing about it that it is achievable if we cannot get more samples. Well, the bad part about that is we need overlap between the training and the query set. Apart from that, we actually gain less understanding about the query set. Well, for active learning, we do not need the overlap and we can gain more understanding about the data we work with. The bad thing about it is that it is not achievable if we cannot get more samples. So I got some good articles here for the covariant shift. If you are interested, you should definitely have a look at them. So the density ratio estimation in machine learning is kind of related to the idea of sample reweighting. And correcting sample selection bias by unlabeled data will give you some insights how theoretically they can eliminate the covariant shift. Thank you for your listening.